A very good welcome to today's session on neurohistology review. It will be more of a virtual practical aspect, or rather a virtual practical approach. So how we're going to do it is I'll be showing you some slides that will attempt to identify, other than just attempting to identify, I'll also expect you to perhaps give a reason why you think it could be what you've said. So what I mean is you give an identification with a reason, and the reason is more of a descriptive support of the identification. If there is one or two things that I'll also want to add on top, largely from a theoretical aspect, I'll add. And if there's one or two things that I think need also to be added, I'll emphasize. That will be the general approach to this session. So I'll start with this slide here, projected to us. I believe you can see it. So how we'll do it is you can give an attempt of a description. Perhaps I take this one up, then now you learn how I want you to do it, then you do it subsequently. So I'm seeing a structure that has been cut in cross-section. The structure is encapsulated, as you can see here. This is the capsule. And within it, I see multiple smaller rounded to ovoid structures, which also appear to have been cut in cross-section, and they also appear to be still encapsulated, although they're within that large thing that is encapsulated. A higher magnification reveals further what I've just mentioned, but also that between the smaller fascicles, we can see some adipose tissue and also blood vessels, as you can see there. So basically, this is largely consistent with how a peripheral nerve looks like. Usually, a peripheral nerve has several fiber processes which run within one large sheath, which you're calling a peripheral nerve. And so these are the various fascicles of the nerve processes that we have within the peripheral nerve. A higher magnification still reveals to you further the adipose tissue and the connective tissue elements that we see in a peripheral nerve. So remember that there is, if we talk about the connective tissue elements of a peripheral nerve, there is endoneurium, perineurium, and epineurium. So endoneurium will be the connective tissue elements that we see within the fascicle there. Perhaps a high magnification will reveal. So this is the endoneurium, surrounding each axon of fiber, as you can see there. And then this is the perineurium, surrounding the fascicle. And then this is still perineurium. And then this is the epineurium, surrounding the whole peripheral nerve. Okay, so that's the slide of the peripheral nerve. Okay, now I'll give you this one. Any volunteer, you just put up your hand, I'll enable your mic, and then you'll give us a description and identification, or identification, then description. Any volunteer? Okay. Let me take that up as well. So this one we are seeing, again, an encapsulated structure. So that the capsule, I'll give you the description, then you'll give me the identification. That's the capsule. That is also the capsule. This is adipose tissue just around it, but not inside. That's the best I can appreciate at this modification. I can see several cells within the capsule with some fibers inside the capsule, but no great detail. A high magnification confirms the presence of the capsule, but it also confirms the presence of several large cells within the capsule, rounded, ovoid, large cells. And we see some fibers interpassed between the cells. Of note is that the cells exist in grouping. And importantly, there's some cells which have an open face nucleus, or what we call vesicular nucleus. Now look at that cell again, that one, this one, that one, that one. This is what we describe as open face nucleus. Now what's an open face nucleus? An open face nucleus is largely a very large euchromatic nucleus with a prominent nucleolus. When we say a nucleus is euchromatic, what does it mean? It means that it has a lot of euchromatin. Now remember there are two types of chromatin material. There is euchromatin and heterochromatin. When you talk of euchromatin, you're referring to the chromatin that is dispersed, the chromatin that is transcriptionally active. Then heterochromatin is the chromatin that is condensed, the chromatin that is not transcriptionally active. So these cells have very large euchromatic nucleus, which means that the nucleus has a lot of dispersed chromatin material that is active in transcription, which means that these cells are actively synthesizing proteins. Then they also have a very prominent nucleolus. That dot you're seeing there that you might think is a nucleus, actually the nucleolus. A very prominent nucleolus. Remember, nucleolus produces ribosomes, or at least ribosome RNA. So again, that is consistent with a cell that is actively synthesizing proteins. So these cells, they are large, many, grouped together, and they have a feature of active protein synthesis and secretion. That is one of the unique characteristics of neuronal cells. Usually neurons have that kind of property. So we have several cell bodies of neurons within this particular zone, interpassed with a lot of fibers, and the whole structure is encapsulated. Look at that magnification. You confirm the presence of open face nucleus, large euchromatic nucleus with prominent nucleolus. Then we have fibers interpassed. Okay, so with those descriptions I've given you, what could be this structure? Remember, it is encapsulated. Cell bodies grouped together, interpassed with fibers. Okay, any attempt? Anyone? I'm looking for a hand up. Feel free to speak so that it becomes even more interesting, more engaging, and also we finish faster. Okay, nobody has attempted. So this is a slide of a sensory ganglion. That's a sensory ganglion. Commonly, you'll be asked to identify something more. And I'm showing a hermatification of it. So we can see cell bodies of neurons there with a very large nucleus, euchromatic nucleus, prominent nucleolus. But importantly, I want you to look at the perimeter of each large cell. I want to confirm that there's a presence of some small cells, again, in the perimeter of each large cell. For example, this one, we can see some cells around it. Even this one, we can see some cells around. So usually, the large cells are surrounded by a ring of smaller cells. Very important to note for a sensory ganglia. A common question we then ask you is, what are the cell types in that sensory ganglia? So we have the cell bodies of pseudounipolar neurons. These are the large neurons, the primary sensory neurons. It houses the cell bodies of the primary sensory neuron. Other than that, the cells which surround the cell bodies of the primary sensory neuron are the ones we call the neurosatellite cells. They provide support to the cell bodies of neurons, sensory neurons. So those are the primary cell types of a sensory ganglion. The cell bodies of pseudounipolar neurons and the neurosatellite cell that surround the cell bodies of pseudounipolar neurons. But remember, these pseudounipolar neurons have some processes arising from them. And so those processes are the ones which constitute the fibers which interpass a sensory ganglion, which you can see here. So these axonal fibers are the ones which attach or arise from the cell bodies of a sensory ganglion. Remember, you may have a cranial sensory ganglion or a spinal sensory ganglion. The spinal sensory ganglion is what we call the dorsal root ganglion. Their structure will be largely the same in as much as one is related to a spinal nerve and another is related to a cranial nerve. Remember, this is the structure that is commonly targeted by the varicella zoster virus. All right, another slide. This one is a cheap one. Anyone to give us a trial on the identification of this one? Just put a hand up, I'll enable your mic. This one, if you don't identify, we skip it. It's very cheap. Yes, Lisa?
This one, we can be able to see the central canal. We can also see gray matter in a H-shaped manner, and the white matter surrounding it, and ventral sulcus and dorsal lateral sulcus. So this one is a section of spinal cord.
All right, very good, thank you. So this is a cross-section of the spinal cord. It's a cross-section of the spinal cord. Very good. And the reasons you've given are very okay, doc, that's fine. So when we talk about spinal cord, some things to note about the structure of the spinal cord. There is a central canal which contains CSF, and surrounding it is a layer of ependymal cells. This is a spinal ependymal lining that surrounds the central canal. Around that is the spinal cord gray matter. This is spinal cord gray matter with the posterior horn and the anterior horn. Also here, posterior horn and anterior horn. Then there is the white matter. Remember, the white matter of the spinal cord has 3 columns: the dorsal column, this region, the lateral column, and the anterior white column there. How do you know the front from the behind? You look at this central median fissure or the central sulcus, which is deeper and central, as the name suggests. So it's the anterior one. Directly opposite is the dorsal sulcus, which is fainter. But a more prominent one dorsally is the dorsolateral sulcus, as Dr. has just said. So this is the spinal cord, this is the dorsal lateral sulcus. A higher magnification around the central canal displays that the spinal ependymal lining is simple columnar, simple cuboidal epithelium. As you can see there, around that is the gray matter. The gray matter behind is the dorsal gray commissure, which joins right and left. And in front of that is the ventral gray commissure, also joins right and left side. A high magnification on the anterior horn of the spinal cord gray matter displays to you these large cell bodies of neurons. A higher magnification displays them. Again, you confirm the presence of open face nucleus. So these are the anterior horn cells of the spinal cord. These are the ones which are usually, again, targeted by the polio virus, and that's why polio causes paralysis. These are the cell bodies of the lower motor neuron. Now, something important to know regarding the spinal cord histology is the organization of the spinal cord gray matter in terms of the lamina. Remember, we have lamina 1 somewhere there, up to 6 somewhere here, in that order. Lamina 1 to 4 is more peripheral, lamina 5 and 6 deeper at the base of the dorsal horn. Lamina 7 is usually around here, and when the lateral horn is present, it's also part of lateral horn. Lamina 8 and 9 are the ones which are largely in the anterior horn, and lamina 10 is the gray matter around the central canal, including the anterior and the posterior gray commissures. So those are the rex laminae of the spinal cord. They are named according to morphological differences and cellularity of the neurons within those regions. They have different functions, and I think from a theoretical perspective, I believe you've done the different functions. I'll just focus on the practical aspect. In terms of the white matter, I've already said that you have the dorsal white, lateral white, and anterior white. Now, it is important for us to histologically be able to determine a segment of the spinal cord. And we use a number of things to determine the segment of a spinal cord. One of the things we can use is the amount of white matter. When the white matter is a lot, then most likely on the upper part of the cord as opposed to the lower part of the cord. We can also use the presence of the lateral horn. When the lateral horn is present, then it means that segment is giving rise to an autonomic outflow. So it's either T1 to L2 segment of the spinal cord or S2 to S4 segment of the spinal cord. The other thing we can use is basically the ratio of the anterior horn compared to posterior horn. Generally, we expect the anterior horn to be slightly bigger than the posterior horn, but when the anterior horn is massively bigger than posterior horn, it most likely represents that that region of the spinal cord is giving rise to a plexus. Now, remember, there is brachial plexus from C5 to T1 for the upper limb innervation, and lumbosacral plexus from L1 to S3 for lower limb innervation. Those segments will have a disproportionately larger anterior horn compared to posterior horn of the spinal cord gray matter. The other thing we can check is the dorsal column, whether the dorsal column has been partitioned into two. When it is partitioned into two, we can say therefore that the middle one is fasciculus gracilis and the latter one is fasciculus cuneatus. If it's not partitioned, we may not say much about that statement because not all the time it will appear partitioned, even if the two tracts are present. But when it's partitioned, then you know that definitely the two tracts are present. Now, when the two tracts are present, what does that tell you? It tells you that we're actually in the upper part of the cord because that's when we have the fasciculus gracilis and cuneatus together. Lower part of the cord will only have fasciculus gracilis because remember, fasciculus cuneatus carries sensory information from the upper part of the body, the junction usually T6 of the spinal cord. Last but not least, you can be checking the presence of collateral spinal nerve roots, which are usually on the side. This represents that we are very near the region of the cauda equina, and that is why you have parallel spinal nerve roots on either side of the spinal cord. And so when you see a lot of collateral nerves, it tells you that we are in the lower parts of the cord. When you don't see them, it doesn't tell you much. Why? Because during preparation, they could have been present, except that they were removed during preparation. So when you don't see them, it doesn't tell you much, whether they're upper or lower. But when you see a lot of them, you are definitely in the lower cord. So those 4 or 5 concepts are the ones that I want us to use to be able to determine the cord levels. And you don't have to use all the 5. Most of the time, actually, with the practice, you'll realize that you just need 1 or 2 concepts to give you your identification of the cord. Let's start with this cord segment. So this is spinal cord. We agree. We can see the butterfly. We can see the ventromedian fissure. We can see the lateral sulcus. The gray matter is central and the white matter is outside. But which cord segment could this be and why? Any volunteer? Yes, Mokaya.
Looking at this section, we have more of white matter tracts than the gray matter. Then both the anterior and posterior gray horns are very thin. And we can actually see also that we have a lateral horn. So most likely this one with the lateral horn, I'll take it to be the thoracolumbar region, T1, L3 there, because of that lateral horn and also the thin, both anterior and posterior, with plenty of white matter tracts.
Very good. Thank you very much, Dr. Mokaya. So you are right that there is lateral horn here. And so that tells us that this region of the spinal cord is definitely giving rise to an autonomic outflow. It can either be T1 to L2 segment, but can also be S2 to S4 based on that account only. And so I like the fact that you've also looked at something else. You've also taken note that the anterior horn and the posterior horn are relatively thin, and I agree with you on that one. And that rules out something, that this region of the spinal cord cannot give rise to a plexus. That is the rule. It cannot give rise to a plexus. And so definitely it cannot be an S2, it cannot be an S3, because those don't give rise to plexuses. Again, most likely maybe not T1, because T1 also gives you a plexus. Very unlikely that it will also be an L1 and L2, because those ones also give you plexuses. So we are remaining either between T2 up to T12, or we are remaining the possibility of an S3, perhaps. Sorry, an S4, not S3, but S4. And so the game changer is on the final thing. The proportion of white matter to gray matter is quite massive here, that there's a lot of white matter compared to gray matter. And that can only tell you one thing. We are on the upper segments of the spinal cord as opposed to lower segments of the spinal cord. So it cannot be S4 definitely. Again, very unlikely that it will be a T12 because of the ratio of white matter to gray matter here. So it's most likely an upper thoracic cord. Maybe not T1, but it's an upper thoracic cord. So for your information, you just say thoracic spinal cord, that is still okay. But now we are learning from concepts that very unlikely to be a lower thoracic because of the volume of white matter that we are seeing here. If you look carefully, you may also see partitioning of fasciculus gracilis and fasciculus cuneatus at that point. So there is a cuneate gracile separation at that point. And that also confirms that we are on upper thoracic rather than lower thoracic. All right, let's try another one. Okay, so this is the next one. Any attempt? Anyone? Just put up your hand. I'll give you a mic. Yes, Raymond.
I can see here that we have a relatively equal amount of white matter to gray matter. But what is remarkable is the predominant amounts of collaterals from on the sides. And also, I cannot clearly distinguish the division of the dorsal columns. It's not overt that the anterior horn is way larger than the posterior horn. So I'm not sure if this is in a lower lumbar sacral area that has a plexus. So from what I've seen, I can say it is either it's an area lower than L5S1, or it is L1, around L1 after the spinal. We have started developing the chorda equina.
Okay, you're very right, very right. It is a lumbar segment, and the reasons you've given are quite good. I like them. Of importance to note is that you've appreciated the presence of numerous collaterals, confirming that we are on the lower segments of the cord rather than the upper segments of the cord. You've also appreciated the presence, or rather the fact that the white matter and gray matter ratio, the white matter is not so much compared to the gray matter. Almost equal. And again, that also confirms to us that we are not so much on the upper cord, neither are we extremely lower on the cord, because the white matter, gray matter is almost equal. Something else you've mentioned that's very key is the size of the dorsal column. It's thinned out, as you can see there. That means we only have perhaps fasciculus gracilis there. We do not have fasciculus cuneatus there. We can't, with a lot of confidence, say whether there is a lateral horn. I quite can't see any. And so then again, it means that it is unlikely to be giving rise to an autonomic outflow. However, again, there's no much satisfaction in terms of comparing the dorsal horn and the ventral horn in terms of the sizes. We can see that the ventral horn is big compared to the dorsal horn, but not so massively to scream about, but at least we can see it's big. So it's equivocal there. Anyway, with the findings that we've stated, this confirms that a lumbar cord. we may not specify which segment of the cord, L1, L2, L3, L4, L5, but it's largely a lumbar spinal cord. All right. This is another cord segment. Any attempt? I'm waiting for a hand up. Yes, Dr. Mukaya.
Looking at this image, we can appreciate the ratio of white matter to gray matter. The white matter tracts look more predominant than the gray. Then, if we look at the horns, especially the dorsal gray horns, these dorsal gray horns look very thin as compared to the anterior gray horns, which is typical to a segment. Then if you look at just medially on the dorsal columns, they are very distinct. These dorsal columns are very distinct, as you can see, could be the gracile and cuneate circular columns rising. So most likely this could be in the, according to me, cervical region, then the head shape.
Yes, you're very right. This is cervical cord. That's
Yes.
very doc, and the reasons you've given actually are fantastic. So one, there's a lot of white matter in this region compared to gray matter. That confirms its upper cord. Two, we can see the dorsal column is distinctly partitioned, fasciculus gracilis and cuneators. And look at the size of cuneators, quite massive. Again, that tells you we are way in the upper cord rather than lower cord. Then I like what you've noted about the size of the dorsal gray compared to the ventral gray, that the ventral gray is quite prominent here compared to the dorsal gray. And that tells you that this region is giving rise to a plexus. So with those, we will narrow down to the cervical spinal cord. And to be more specific, it is most likely a lower cervical rather than an upper cervical. The reason is because of the presence of the giving rise to the brachial plexus, evidenced by the size of the ventral horn. So it's most likely lower cervical rather than an upper cervical, because upper cervical doesn't have the brachial plexus. Anyway, for the sake of examination, you just talk about cervical cord. The last one is a sacral cord. And we can see evidenced by the fact that the gray matter is quite predominant compared to white matter, which is hardly there. That tells you extremely low in the cord. Look at the size of the dorsal column. Very thin. You have to squint to see it. The white matter is very thin, but the gray matter is quite a lot. So that confirms to you, you are extremely low in the cord. We can see some collaterals. We can't really scream that there are a lot, but at least you've seen them. So we may not use that point to confirm that it's lower cord, but at least you've seen them and seen how they look like. So the most important thing here is the gray matter, white matter ratio. That tells you lower cord. This is sacral segment. Okay, so those are spinal cord. We have another one here. Any attempt for identification for this? Yes, Raymond?
So I'll start by identifying, then I'll give my reasons.
Okay.
This looks like the lower medulla, which is regarded as I'll argue that it's the closed medulla. So I'll start anteriorly, like, okay, ventral, on the lower side of the slide, those look like the pyramids. They have stained blue because that's how the axons stain. So those look like the pyramid. Just behind the pyramids is the olives, the bilaterally, the large, the things that are not what you have just labeled. Perhaps between the olive and the pyramid, you can see some fiber roots exiting from a nucleus. Those we learned that, I think that's hypoglossal nerves, the hypoglossal, but we will comment, doctor will clarify. So medial to the olives, you can see, I think these are lemniscus, medial to the olives. There's a meniscus. Then just as you go posteriorly, and even more to correlate with our theories, the two nuclei. This in the middle one, this one will be what? This will be gracile nuclei. I'm not sure if I cannot comment. It could be gracile nuclei or it could be other things. But there's a nuclei there. Let me say that. What else posteriorly? Here where doctor is pointing behind it will be. I'll leave it at that. Doctor, that's what I can be able to see. There are various nuclei.
Okay, that's okay. We don't have to identify the smaller nuclei, don't worry, that's very good. I like the description you've given. Let me have an addition from Jennifer. Yes, Jennifer?
Am I audible?
Yes, but you can tell people around you to lower their mic. Is it okay now?
Okay. Hello?
Yes, Jennifer, we can hear you now.
Hello?
Yes, we can hear you. Jennifer, we can hear you now.
Oh, okay. You can hear me?
Yes, but I think you have multiple devices around. If you can lower the volume of the other devices, it would be better. Is it okay now?
Said another one.
Okay. Oh, yes. You can go now.
Okay. Yes, so I wanted to differ with Dr. Kibaso in terms of whether it's open or closed. It looks like it's open medulla.
Okay.
You can see the presence of the fourth ventricle with the periaqueductal gray matter surrounding it.
Okay.
And then also the presence of the convoluted inferior olivary nucleus shows that it's upper medulla.
Okay, good addition. That's an important addition. Thank you. So we can consolidate what you have said with what Dr. Kibaso said, and we can then agree. So I agree with Dr. Kibaso on the fact that these are pyramids and this is the inferior olivary nucleus and this is the lemniscus, this is the medial lemniscus system and this is the mid-longitudinal fasciculus. We have some cranial nerve nuclei there. We don't have to go into the details. And then I agree with Dr. Jennifer that this is actually the fourth ventricle. So if it's ventricle, then you call this one periventricular gray. So with that, we will go with the open medulla, which is upper medulla. So remember that when we use the term closed medulla, it means that the spinal cord, the medulla oblongata has enclosed the ventricular space. There is tissue of medulla around the ventricular space. In other words, it has a central canal. This one doesn't have a central canal. this one has the fourth ventricle. So as long as the fourth ventricle is an open medulla, and you know it's open medulla by this open book appearance of the fourth ventricle with periventricular gray. Then coming ventrally, the pyramids are distinct with a very deep cleft, and posterolateral to that, we see the large, highly convoluted nuclei, which the two have both correctly identified as the inferior olivary nucleus. So this is slide of open medulla or upper medulla. You may have seen some fibers coming off. These ones, these are the internal arcuate fibers coming, and they seem to come from somewhere here. So if you are able to see cuneate and gracile nuclei, they'll be somewhere here, not here. Remember, when the fourth ventricle, the nuclei are very close in the midline, will be hypoglossal nucleus and perhaps dorsovagal nucleus, slightly closer to that one. All right, this is another slide of the CNS. Any attempt for this? All right, Dr. Mukaya.
Okay, let me try. The most distinctive feature is this, when we look at anteriorly, it looks like this is the section of the medulla, and it's now closed medulla, I can say. Closed medulla, then there is, we can see the periventricular gray matter around the ventricles, it's closed. Then anteriorly, the pyramids are distinct. I think the pyramids are distinct as compared, yeah, generally I can see the pyramids distinct. Then I'm not sure about the just posterior to the pyramids and anterior to that ventricle, we can see another bluish black substance. I don't know if that is the medial. So me, I'll take this section. The only thing I can see is the distinct pyramids, meaning this is at the level of the sensory decussation. Yeah, sensory decussation, because the pyramids are distinct, they are wide apart. They've not crossed. The rest of the structures are honestly, I don't know. I can only see the medial longitudinal fasciculus and those distinct pyramids. I don't know the rest of the structures.
Okay, that's fair enough. Good trial. Let's hear an addition from Kenneth.
I don't know if that it can be heard. So
yes, you can be heard well.
Just to add on what Mokaya has said, you can see that there are the pyramids on the yes, and then you have identified the medulla. This is the medulla. So the blue darkish fibers that he was referring to are actually the decussation, that is the pyramidal decussation at the level of the closed medulla. And then also you can identify on the posterior end, you will find that there's some bluish, there's some bluish, and also there's some lightish, I don't know what to call it, but those are the fibers of the gracile fasciculus that are medial, and then the ones where there, and then the where you're pointing is where the cuneate fasciculus is. So I think we are at the level of the closed medulla. That is all I can identify. Thank you.
All right, very good. Let's hear one last addition from Humphrey. Humphrey, you can unmute yourself.
Hello.
Yes, Humphrey.
Thank you. I'd say this is the closed medulla above the point of motor decussation. the structures have been correctly identified by my colleagues. The pyramids are ventral. Where the pointer is currently, that's the medial lemniscus forming. You can see the fibers, the arcuate fibers are actually coming towards the medial lemniscus. And as we go, you can see there's a pericentral gray and the central canal, which now indicates this is the medulla. Going more dorsally, we find the fasciculus cuneate and the fasciculus gracilis with their nuclei. The whitish parts, which we couldn't identify, were the nuclei for the cuneate and gracilis nuclei, and slightly below it, more lateral, that's the trigeminal, the spinal trigeminal tract and nucleus. Yeah, I think that's it.
All right, very good. Thank you very much. So now 3 speakers have given us their comments, and we can now narrow down. So yes, we are talking about this medulla oblongata at the level of sensory decussation. So important to note is that the moment you can see the internal arcuate fibers, then this cannot be motor decussation. It is sensory decussation. And so this is medial lemniscal system. The pyramids are still very distinct. The inferior livery nucleus is partly there, partially there. That's part of inferior livery nucleus. Then this is the pericentral gray matter. The central canal is actually collapsed. We can't see the lumen, but this is pericentral gray matter. So it is closed medulla. And as they have correctly said, this is the nucleus gracilis with fasciculus gracilis. This is nucleus cuneatus with fasciculus cuneatus. And this is trigeminal, the spinal nucleus of trigeminal with the spinal tract of trigeminal next to it. Spinal nucleus of trigeminal with the spinal tract of trigeminal. So this is closed medulla level of sensory decussation. Compare with this one, which is now closed medulla level of motor decussation. Of importance to note is that the butterfly that we expect to see for spinal cord is not coming out clearly. However, we have a truncation of the anterior horn. So that there's a nucleus here and there's another nucleus there, and there's white matter in between, truncating them. This white matter truncating them is actually the motor decussation of the pyramids. Dorsally, we can see fasciculus gracilis and fasciculus cuneatus distinct there. So the level of motor decussation, we don't see the olive. We don't see the sensory decussation. It is closed medulla way down at the spinal medullary junction. And so this is the closed medulla. That's how it looks like, closed medulla level of motor decussation. Okay, I'm showing you another series of slides here. So these are slides of the midbrain. Why do we think the midbrain? We can see the characteristic. Oh, there's a question from Liz, I think from the previous one. Liz, yes, you can ask.
I was commenting on the slide.
Okay, yeah, carry on. Thank you.
It's a brainstem histology because of the characteristic box short appearance generally. And then we can see from dorsal coming back, we can see cerebral aqueduct with the periaqueductal gray matter. And then we can see crus cerebri ventrally. Yes, crus cerebri ventrally. Next to it, there's a lemniscal system. And then I'm not sure whether you can see it this is the red nucleus, but with that, it becomes the brainstem histology.
All right, thank you very much. So it's brainstem, I agree with you, but more specifically, midbrain. Midbrain, yes. So yeah, I agree with you, Liz, thank you. So for midbrain histology, the things that Dr. has mentioned are very correct. The aqueduct, periaqueductal gray matter. Whenever you see this characteristic shape, boxer shape, it becomes very characteristic for the midbrain. And then now we mention a number of things. So this is the tectoplate. It could be superior colliculi or the inferior colliculi level. This is the level where you expect the red nucleus to be. And now mark something. You can see that this one and this one are slightly separated by something here. But when you compare the second one, this one and this one are not separated. That gives you a clue on which part of the midbrain we're talking about. So where you see the separation, it means that you're most likely in the upper midbrain. And so the colliculi here are most likely the superior colliculi. But when you don't see the separation, you're most likely in the lower midbrain. And so what we are seeing here is actually the decussation of the superior cerebellar peduncle, instead of here where you're seeing the red nucleus. And that means that if this is the decussation of the superior cerebellar peduncle within midbrain, then this one is the inferior colliculi. And if these are inferior colliculi, then the nucleus you're seeing there is the motor nucleus of trochlea. This is a trochlear nucleus, as opposed to the nucleus you expect here, which is the oculomotor nucleus. The other things tend to continue to stand out. This is the substantia nigra, and this is the crus cerebri. Remember the fiber organization, the crus cerebri. You can divide it into some thirds or sixths. The medial 1/6 carry fibers from the frontal cortex to pontine nuclei. So we call those frontopontine fibers. The lateral 1/6 carry fibers from the cerebral cortex to the other part of the cerebral cortex other than frontal cortex to the pontine nuclei. You can talk about paratopontine, temporopontine, and occipitopontine. If you take 1/6 here and 1/6 here, you remain with 2/3 in the middle. The 2/3 in the middle is the one that carries the pyramidal system. Remember, pyramidal can either be corticospinal or corticonuclear. Corticonuclear targets the nuclei of cranial nerves, number 3, 4, 5, 6, 7, and nucleus ambiguous and the hypoglossal. That's what corticonuclear targets. Corticospinal targets the spinal cord gray matter. Out of the pyramidal, the corticonuclear is on the medial aspect and corticospinal is on the lateral aspect. Great, you can see some nerve coming out ventrally there. So this should be the third cranial nerve coming out. That's oculomotor nerve coming out. This is the lemniscal system. Remember that we have several lemniscal systems: medial lemniscus, lateral lemniscus, spinal lemniscus, and trigeminal lemniscus. So we have all of them there, apart from perhaps the lateral lemniscus that is not within that particular region. This is showing you the slide of Pons. Now that's the only brainstem that we not talked about. So how do we know this is Pons? It's quite characteristic about the zonations. Let's start with the first slide there. the ventral side and the dorsal side are slightly different. The dorsal side is relatively compact, and the ventral side is not as compact. It is important that you first locate the fourth ventricle before you start orienting yourself. So in this slide, this is the fourth ventricle. And in this slide, this is the fourth ventricle. If this is the fourth ventricle, then whatever you see behind here is not Pons. This is part of cerebellum, but this is Pons. In this one, the whole of the slide is Pons, but on the second one, only the lower part is Pons. The dorsal part is not Pons. This is cerebellum. You can even see the dented nucleus of the cerebellum there. Anyway, so focusing on Pons, the dorsal part of Pons is called the pontine tegmentum. This is the most compact part. It contains a number of things: cranial nerve nuclei, the lemniscal systems, reticular formation. They are found within the pontine tegmentum, and this is continuous, the tegmentum of midbrain. Then the ventral aspect is what we call the basal pons. Basal pons contain three major things. One, the decasseting fibers, which come from pons to go to cerebellum. So you can call them the decasseting pontocerebellar fibers. You can see they're running transversely. So they're here and they're here. The second thing that is found within the ventral pons are these locules here. These are locules of dispersed corticospinal tracts. So the corticospinal tracts or the pyramidal tracts which are dispersed within the basal pons. So when they come from midbrain, they are within the crus cerebri. When they pass through Pons, they are scattered. And then when they go to the medulla, they consolidate again as the pyramids. So these are the dispersed corticospinal tracts. The third component, which is found in the basal pons, are some nuclei which are found within the transverse fibers. You need a high amplification to see that. Those are the pontine nuclei. So remember, the pontine nuclei are part of this big system from the cerebral cortex to Pons to cerebellum, the cortico-pontocerebellar fiber system. A common thing you may be asked is to identify this structure seen here. So this is the facial nerve as it acts behind the abducens nucleus. So that's the abducens nucleus. And this is the facial nerve coming out. So that's Pons. Okay, I'll give you another slide. We will finish them, but you'll have to give me up to maybe another 20 more minutes, you'll be done. So this is another slide. Any volunteer for this? Yes, Lisa?
This slide, we can see various cells transitioning from the left to right without distinct layers, but at the end they have transitioned, and then there are also some fibers crossing. So this one I would say is the cerebral cortex.
Very good, you're very right, and I like that description, very honest, and it's the one that actually helps. So this is the slide of the cerebral cortex. As she's mentioned, we can see cells transitioning. You cannot see a distinct junction of transition. You can't say it is here, it's at this point, you cannot. We don't have sharp transitions, but we have progressive transition. The transition we're talking about here is the transition regarding the cellularity, but that may not be very distinct, but also transition regarding the shape of the cells. As you move from left to right of the screen, you see that the cells on the left extreme are tinier, and the cells on the right extreme are slightly bigger, or at least they increase in size to some level. That's important. The other important thing to mention is the fibers that she's talked about, the ones that tend to stain blue. Those are axonal fibers coming in. So that confirms to you again that you are in the central nervous system. Now we can add something more that confirms that this is actually cerebral cortex. One is just the cellularity. The fact that it's highly cellular, it means the cortex. Remember, cortex is highly cellular, and that the cells are in varying zones, or rather, let me say they're in changing transitions of shapes of cells or size of cells, something like that. The other important thing to mention is that you can see a surface, a thin membrane on the surface that is consistent with pia mater, and external to that, you can see blood vessels consistent with the blood vessels within the subarachnoid space. The other thing you can mention, look at around this region, you can see some characteristic triangular shape, kind of prominent cells with triangular shape, confirming that you're looking at the giant pyramidal cells of Beth's within that zone. So this is the slide of the cerebral cortex, and those features I've given you are the ones that we use largely to identify the cerebral cortex. Remember, in terms of the cerebral cortex, the main neuronal cell type of the cerebral cortex, the output cell, is the pyramidal neurons, and this slide shows you how the pyramidal neurons look like. At higher magnification, these are the pyramidal neurons. I want you to know something about the pyramidal neurons in terms of its parts. First, it has a pyramidal shaped cell body. And then this long thing, this is arising from the apex. It is very tempting to call it the axon, but it is not the axon. A pyramidal neuron, and these ones are better, has a pyramidal shaped cell body or a triangular cell body in 2D to be triangular. Then it has a long apical dendrite. So whatever is arising from the apex is a dendrite, not an axon. And that dendrite has other secondary branches, fine. But that's not the only dendrite. It also has basal dendrites and a basal axon. So in this one, perhaps this is the axonal projection. Most of the other basal structures are actually dendritic. Or this other image shows you long apical dendrite with secondary branches. The basal side, we have still dendritic branches, but we also have an axon from the base. Remember, the pyramidal neuron is the output neuron of the cerebral cortex. I want you to also remember the layers of the cerebral cortex that are not well defined, but we can talk about them. And importantly, to know what happens in each layer. Layer 1, the molecular layer, is largely a synaptic zone. Layer 2, the outer granular layer, is the one that receives, it's an input from other cortical regions. That means that it receives a commissural and association fibers. It's the point of termination of commissural and association fibers. A commissural fiber is the one that comes from another cortical region. Association fiber also come from another cortical region. Wherever they come from, they terminate in layer 2 at their destination. Layer 3, the outer pyramidal layer, is the one that gives rise to the commissural and association fibers. So an output that comes from one cortical region to another will begin from layer 3 and then terminate in layer 2 of the destination. Layer 4, the inner granular layer, is the input center to the cerebral cortex from subcortical region, primarily from the thalamus. So it's a thalamic input center. neurons that come from regions outside the cerebral cortex terminate layer 4 of the cerebral cortex. And so based on that, we can say that's the cortical input center. Layer 4 is the point of termination of the projection fibers. Layer 5 is the point of origin of the projection fibers, largely giving rise to the cortico-spinal, cortico-bulbar tracts, or corticothalamic. It's the output center from the cerebral cortex. Layer 6, the multiform layer, is an interface between the gray matter and the white matter. So it has mixture of fibers and neuronal cell bodies in almost equal measure. So those are the layers of the cerebral cortex, and perhaps the key function for each of the histological zone. As you can see, very difficult to say the junction is here to here, not well defined, but highly cellular. I've already given you that description of what happens in each layer. Okay, let's try this one. What could this be? I want you to look at this on your left and then identify this one on your right. For you to identify this thing on your right, you must first see what is on your left. But what you're identifying is this one on the right. What could it be? Any attempt? Okay, sounds difficult for majority. So look. All right, Raymond wants to try. Yes, Raymond.
The choroid plexus or something.
Yes, actually, you're right. This is the choroid plexus. And I was about to tell you that you can see it is highly folded, lined by one layer of cells, simple cuboidal epithelium, with a very vascular core. We can see loose connective tissue or loose tissue at the core, but highly vascularized. As you can see, these are blood vessels at the core, lined by simple cuboidal epithelium, highly folded within a space. And then adjacent to it, you can see one layer of ependymal cells, and we can see CNS tissue there. So this is the ependymal lining, and this is the choroid plexus within a ventricle. All right, this is very magnificent. The slide of the cerebellum. Let me just take it up because of time. So this is the slide of the cerebellum. What is important to note is that you can see the arbor vitae branch like a tree. Look at that white matter branching like a tree. Very fantastic. And of note is that as you go peripherally, the white matter becomes thinner because it's branching. That's the arbor vitae. The arbor vitae is surrounded by some layering, very characteristic layering. There's that layer and there's that layer. And then it is highly folded. The folds of the cerebellar cortex are termed folia. So it's foliated. Now let's go deeper into the magnification and see what constitutes the cerebellar cortex. At low magnification, you only see two layers. There's this layer, the molecular layer, and there's this layer, the granular layer. Those are the only layers you see of the cerebellar cortex. Remember, this arbor vitae is not cortex, it's white matter. So yes, you can see three layers, but the innermost layer is white matter, not cortex. So for the cortex, you only see those two layers, the inner granular, outer molecular, at this magnification. But if we increase the magnification, we may start seeing something in between the two with that cell body. And perhaps a high magnification reveals them. We can see cell bodies of the Purkinje neurons. And so we talk about the outer molecular layer, the inner granular layer, but the middle Purkinje cell layer. Purkinje, not pyramidal, Purkinje cell layer. So histologically, the cerebellar cortex has 3 layers: molecular, Purkinje cell, and granular layer. In terms of the histologic organization of these layers, this molecular layer contains basket cells and the stellate cells. The granular layer contains the Golgi cells, the granule cells that are found within the granular layer. The Purkinje cell layer contains cell bodies of Purkinje neurons and also the Bergman cells. Remember, the Bergman cells are like astrocytes in the cerebellum. So their cell bodies are located in the Purkinje cell layer. The Purkinje cell is the output neuron of the cerebellar cortex. It looks like that. Characteristically, it has a round, the cell body is like a round bottom flask. And then it has extensive dendritic arborization, as you can see there. And then it has a basal axon. So the dendrites of the Purkinje neurons are the ones in the molecular layer. The cell bodies of Purkinje neuron are the ones in the Purkinje cell layer. The axons of Purkinje neuron are in the granular layer. That distinction is important for you to be able to understand cerebellar connections. So in terms of cerebellar connectivity, neurons enter the cerebellum. They project into the cerebellum. And then there's some connections within, then there's an output. So let's start with whatever comes in. The neurons that come into the cerebellum are grouped into 2 based on how they connect to the cerebellar cortex. The ones which come from the olivary nucleus usually project all the way, they go through the white matter, then the granular layer, then Purkinje cell layer, and all the way to the molecular layer, to synapse with the dendrites of Purkinje neurons. Those ones are termed climbing fibers. They climb all the way to the molecular layer without synapsing. They only synapse directly with the dendrites of Purkinje neurons. We call them climbing fibers. So that's one category of cerebellar afferents. The second category of the cerebellar afferents are basically the afferents that come from anywhere else apart from olivary nucleus. So they could come from the pontine nuclei, they could come from the vestibular nucleus. Wherever they come from, they may come from the cunate nucleus. Wherever they come from, they enter the arbor vitae and then make a synapse within the granular layer. So there's some relay. The point of relay within the granular layer is very characteristic, because at that point of relay, there could be a lot of conglomeration of many neurons synapsing at that point, constituting what we call the Mosey fiber rosette, or the cerebellar glomerulus. And so the fibers of cerebellar afferents that relay within the granular layer constitute what we call the Mosey fiber system, which is the second fiber system, the Mosey fiber system. The Mosey fibers relay within the granular layer. The conglomerate of the relay is what we call the glomerulus, or the Mosey fiber rosette. From that relay, there are some neurons that now take their axons all the way to the molecular layer, and you can see that they divide so that now they can synapse with the dendrites of Purkinje neuron, which are within the molecular layer. From that, as we have learned before, that now the Purkinje cells are now the output neurons from the molecular layer. The axons of the Purkinje cells project primarily to the cerebellar deep nuclei. There are four: dentate, globose, emboliform, and fastigial. Generally speaking, the Purkinje neurons, which come from the cerebellar hemispheres, will project largely to the dentate nucleus. And this constitutes really the function of what we call the neocerebellum. That is the neocerebellum. Largely, those fibers may have come from multiple places, but that's the neocerebellum. Then we have this other entity, the Purkinje neurons, which project from the flocculus and the nodule. These ones, they came from, or rather, let me put it this way. The Purkinje neurons, the dendrites are within the flocculus and the nodule. The Purkinje neurons from those regions project into the fastigial nucleus. So that the fastigial nucleus is the output nucleus from the flocculonodular lobe. This is the lobe that is related to the vestibular function. So it's the vestibulocerebellum, or others known as the archicerebellum. Then the Purkinje neurons from the vamo region, paravamo region, and anterior anatomical lobe and the tonsils. Those ones project largely to the fastigial and emboliform, and they constitute the paleocerebellum. All right, so in a nutshell, remember that there are two major types of cerebellar afferents: the climbing fiber system and the mossy fiber system. Some people describe the monoaminergic afferents to the cerebellum as a distinct entity. It's fine, but I think the point here is that if you look at it from a structural point of view, there are only two: mossy and climbing. But when you look at it from the type of neurotransmitter, then you can have a unique entity that we call the monoaminergic system, that come from the brainstem reticular formation, including the regions of the locus ceruleus, and project in the cerebellum. They have a unique function to the cerebellum. All right, thank you very much. So I have tried to capture all the slides that are required in neurohistology series, and I think we've done justice to it. I think that should be it, unless there is a question.